So in particular, some of the talks here have been on very abstract objects. This series of talk will be at the opposite end of the spectrum. It will be very down to earth. Okay, maybe tomorrow I will even write down some n by n matrices where n is some large number. Okay, so anyhow, the plan for these two lectures, at least my original plan was that this lecture I will talk about a classical technique of Theta Correspondence, and then tomorrow I'm going to talk about D and D, doubling and descent. But a couple of days ago, as I was walking to IHES with a bunch of number of participants, and someone then asked a very simple question, okay, and I feel compelled to change my plan a little bit and begin by addressing this very simple question. So here is the simple question. How do you know there are non-zero Cusp forms? Okay, I guess, for the young people here, before you devote the next 40 years of your life to this area, maybe, it's good to know that there are non-zero Cusp forms. Okay, so in fact, so I feel that it's necessary to start with a discussion of a very simple construction called Poincaré series. Okay, so what is Poincaré series? It is a map, let's call it P, from, so actually, let me say, I will assume for this part, right, G is a split semi-simple over Q. Of course, if a group G is anisotropic, you can take the constant function, which is, of course, the trivial representation. That is cuspidal because there are no parabolic. So it is so there are there are non-zero Cusp forms. Okay, so so what is this construction? It takes as input comparis for the locally constant functions or smooth functions on GA, and it's going to produce, let's say, functions on there. Okay, and it's very, very simple-minded idea. So you want a function which is left invariant under GQ, so let's just average over the group to produce some functions. Okay, and I guess this map is even G equivariant, with the right translation action of G. Okay, so now point is now given a F. You want to show this guy, for example, is a non-zero Cusp forms. So which F should you pick? So maybe let me use the board, just optimize the board a bit. So which F to use? And going to give you a F, which is a product of local ones. Okay, so here's how I'm going to define it. So let's fix a prime P. So over here, let's fix a prime P and a supercuspidal representation pi of GQP. Okay, of course, now you will ask, you will change this question a little bit, right? How do you know that there are supercuspidal representations of GQP? Okay, I guess this question will be extensively discussed in Jessica Vincent's talk tomorrow. Okay, and of course, we will come back to it in a few minutes. So, okay, so having fixed P, you're going to take here a matrix coefficient. This is pi, okay? If V is equal to P, so at a place you take a matrix coefficient, V is some vector, okay, in pi. At V not equals to P finite, maybe you just take the characteristic function of GZP. There's the Archimedean place, infinite place. Here, you're going to take some functions to be decided later.
You say V is a vector and V is equal to...
Yeah, that's true. Yeah, so let's change it to W. Okay. Yeah. Okay, thank you. Okay, so this one, to be chosen later. Okay, so maybe I should say that the point is that even though this is an infinite sum, actually the sum is finite. Okay, so the reason is because for any fixed g, this thing is finite, right? Because this is some compact set and this is discrete, so the intersection is compact and discrete. Okay. Sorry?
You mean ZV is the second line? FV is...
Yes, correct. Yes. Sorry. Yeah, okay, so all right, so then the point is that by making, so you're going to choose f infinity to be a bump function, okay, something like that, okay. By making the support of f infinity sufficiently small, you can make this GQ intersect the support of F to be just the identity element of the group. Okay, and so this means that this PF, if you use this particular F, its value at 1. So its value at 1, I mean, even though there's, it's a sum, but there's just one term, which is just identity. So it's F1, and that's not 0, okay? Okay, so at least we know it is not 0. So this means that we have a non-zero vector. Well, function is completely supported, so it is certainly in L2. Okay. And now you use the fact that at your place, right, P, pi supercuspidal will imply that all constant terms of PF vanish. Okay? And so in particular, PF is a non-zero Cusp forms. Okay, so that answers the question. Of course, you can do a spectral decomposition of this. You can write this as a direct sum of irreducibles, and you get different components. So when you so if capital pi is an irreducible summand of the span of this Poincaré series within L2 cuspidal, then this has the property. So this is an irreducible cuspidal representation, and it has the following property. So it is a restricted tensor of local representations. So at pi p, it is pi. Pi v is unramified for all v finite, not equals to p. But at the Archimedean place, because you have picked the function rather kind of randomly, okay, so you have no information, so to speak. Okay. So in any case, such a pi is we call it a globalization of the little pi. Okay. And it is useful to, so this construction, even though very simple-minded, but it is useful because it allows you to globalize a given supercuspidal, okay, to be a local component of a global cuspidal. Moreover, with very good control at almost all places. I mean, it's unramified, except it has infinity. Okay, so this type of globalization is useful because sometimes you want to prove a local theorem about supercuspidal, and there are many cases where such proofs are very hard to give locally, and that you might use a global argument to deduce this local statement. Okay, and that's in that context, it is useful to have such globalizations. And for such applications, it's important that you sort of understand the other places, right? You cannot get, I mean, you hope to use your knowledge at all other places except P, together maybe with some global product formula or something like that, to deduce information at P. So it's important to have control at all the other places. So here we have very good control at all other finite places. At infinity, we have no control. And so at infinity, you better prove your local theorem directly. Okay? Okay, so that's the, all right, let's see. Now,
so is it not possible to control an infinite place?
you can, I mean, so this is the primitive version, and maybe with some more refinement, you know, of course, people can mistake. Okay.
Is there Poincaré series for what you define standard, or is it usually used for Whittaker?
Yeah, I think this is even more basic than Whittaker, because
But the term, I mean, is the term Poincaré series?
in the context of, let me see how to move this up in this way. When you, I mean, the context of classical modular forms, where you take a, you know, e to the 2 pi I z and you average over, right? Yeah, so that is a Poincaré series, that is a Whittaker function version. Yeah. So you can, I'll remark about it, yeah. So this one just ideals nothing in some sense. Okay, so now, of course, as we say, this leads to the following question. Okay, by the way, I want to say that if you vary P, okay, we choose a P, right? Then you're going to get infinitely many Cuspidal representations, okay? All right, so now, of course, but you know, we sort of like leads to another question, right? So how do you know that there are supercuspidal representations? Okay. Okay, actually, it's not bad. We go from a global question to a local one, right? That's progress, I guess. Okay, so I guess tomorrow you hear a lot about this, but for today, let me just produce one. And I guess the simplest way to do that is to take a Cuspidal representation of GFP, okay, let's call it tau, and then you set pi to be the compact induction of tau. So you can pull back, you know, tau to GZP, right? That's a surjection. And then you do compact induction. And this thing is an irreducible supercuspidal of depth 0. So okay, so there are supercuspidal of depth 0. Of course, now you ask, how do I know that there are cuspidal representations of F? Okay, and well, I guess the short answer, going back to before Corvallis, is because the linear acoustic tell you so. Okay, you look at what they are called these RT datas. Okay, their paper in 1976, so just before Corvallis. Okay, so that is you know, some answer to that simple question. Okay, let me make a few remarks. Of course, there are variants of this construction. One of them, you know, for example, you can do the following. So if, say, you have a reductive subgroup and pi is H distinguished, meaning pi has a H invariant functional, then you know, a variant of this Poincaré series argument tell you that there are globalizations, capital pi or little pi, such that pi is globally H distinguished. Okay. Of course, the reductive is not really necessary. If you take a maximal unipotent subgroup, okay, you can take a generic representation, the one that has a Whittaker functional. A variant of this argument will produce a globally generic, and that is what Yannis was asking about. Okay, and I guess a good place. This was used by Dipendra Prasad and Schuspillo. Okay, that's one remark. Second remark, maybe I squeeze it over here, is that this does not quite work for discrete series. If instead of supercuspidal, you take a discrete series pi, it doesn't quite work because we need compactly supported function as input. If we try to take the matrix coefficient, right? For supercuspidal, the matrix coefficient is compactly supported, but for discrete series, it is not. So this sum, you can of course try to put in a non-compactly supported function, but then there's no trivial reason why the infinite sum converges, okay? All right, so, but in this case, still using Poincaré series, but just using a little bit more input, so Poincaré series plus inputs from a unitary representation theory. So, I'm thinking of things like Feld topology, weak containment. I don't know how to classify this type of results. These are like unitary representation theory, okay, developed by Mackey and others. Still implies globalization in some cases at least, okay? And this, you can read about this in the asterisk volume of Sakularitis and Venkatesh. Okay, they have a very nice argument that uses some inputs like that, okay? Still allow you to globalize a discrete series. Okay. I have one other remark, so let me see if I can squeeze it here. Okay, so I want to make a remark about relation with trace formula, okay? Because if you recall, if you take a compactly supported functions, like the input for a Poincaré series, there is this automorphic kernel, which is the starting point of analysis of the trace formula. Is that, okay? And then, for trace formula purposes, maybe I migrate over here. Right, so we have this KF. Then you can do various things to it, okay? So for example, you can integrate over the diagonally embedded GA, then this is, you get the trace formula, right? You can take a subgroup. So basically, you are taking subgroups of G cross G, okay? So you can take two subgroups like H1 and H2, and you can, integrate over H1 for X and H2 for G, and what you get is relative trace formula, okay? Now, what I want to point out is that, this Poincaré series basically it is automorphic kernel if you take X to be 1, okay? Right? I mean, it's the same formula, okay? So in that sense, right, you can say, okay, it's just an instance of this second arrow where you take H1 to be the trivial group, okay? And you don't do the integration over H2, okay? But anyway, so in that sense, you can see this very simple argument as like a extremely simple form of the trace formula, if you wish, okay? And the point is that if you would like to, if you use these more sophisticated forms, okay, you can surely prove better results. For example, one typical use of trace formula was to prove Wow's law, right? To count, cuspidal Hacker eigenforms whose eigenvalues up to some t, okay, and how that grows as t grows, okay? And indeed, that was how the trace formula started, right? That Selbert sort of developed the trace formula to answer the questions, are there non-trivial mass forms, Okay, so level 1, so SL functions of SL2R over SL2Z, which are eigenfunctions, maybe even of SL2Z, eigenfunctions of Laplace operators. Okay, so how do you know these things exist? Okay, now this argument here, this answer I give here, right? Recall that I don't produce level 1 Cusp forms, okay? Because I have one place where it's supercuspidal, right? Not to mention I lose information on F pi infinity, but I always have some level because of the supercuspidal. Okay, that's what I'll discuss about Poincaré series. Okay. How should this work? Let's take this down. Okay, now I move on to Theta correspondence. Yes.
So here you use that G is unramifying because you use some integral structure to induce. Is that can this be modified?
Yeah. That's not necessary. I said G was split so that I can talk about these things without, further comments. Yeah, it's not an issue. You can take G to be any group. Okay. Now I'm going to talk about Theta correspondence. So in Covalis, there were like 4 articles on Theta correspondence, okay? And I guess the highlight of those 4 articles is the article of Howe and PS in Covalis, where they produced the first known counterexample to the naive extension of the Ramanujan conjecture that every Cusp form is tempered for a split group, let's say. Okay. Yeah, Piatetski-Shapiro. Yeah. Okay. Okay. So they what do? By using Theta correspondence, they constructed a lifting, so a map. So let's fix E over F quadratic extension of number fields. What they did was they constructed Hacker characters of E cross, but let's assume that they are trivial on F cross. So by which I mean automorphic characters on the adels of E cross, but trivial on the adels of F. Okay, which are doesn't factor through the norms. Okay, so not factoring through norms. Which means not obtained from base change, that's right? 2 Cuspidal representations of SP4. Okay, they produce such a map, which is an instance of Langlands functorial lifting, if you wish. But the point was that the Cusp forms they get here, they get non-tempered Cusp forms. Okay, and this violates these are counter examples to the Ramanujan conjecture, because I guess even at the time of Covalis, the general belief was that every guy here is tempered. Okay, so this was quite a surprise at that time. All right, so okay, I should prove it's okay to do this because we have finished with this discussion. So, okay. Okay, so anyway, I just want to give introduction to this method of construction. Okay, so the general framework, let me just start with some general framework, which is very easy to understand. The framework is this. You have 2 groups, G and H, and their direct product mapped to another group E. You have a representation omega. So this would be like in the local field setting, right? And then you just want to pull back. You want to understand the spectra. How does this decompose, right? So you want to know the spectral decomposition of this pullback. Okay. Now you take any representation, it is going to give you a correspondence. And this is the correspondence in the name Theta correspondence. Okay, namely a subset of the product of the irreducible representation of both groups. Which subset? Those representations, those irreducible representations which occur as quotients. Okay, now, so that you can do this for any, it's completely general, but the ideal situation that you would like to have was that this correspondence is the graph of a map. Let's call it theta omega from, say, irreducible of G to irreducible of H. Okay, that's the ideal situation. If you just pick a random thing, it probably won't work. Okay. So what do you need for this to have a chance of this happening? Basically, a rough, very coarse heuristic is that this representation omega should not be too big. Okay, why? Because if it was so big, when you restrict to G cross H, many things will appear. Right? Many things has to appear just to make up the dimension, all the space there, right? And so maybe everything appears, let's say, then you're not going to have this ideal situation. On the other hand, you don't want to take it to be too small either. If you take it to be the trivial representation, maybe something like this holds, okay, but it's not very interesting. Okay, so you kind of have to take maybe, so you start with the trivial, okay, it doesn't give you something interesting, then maybe you go to the next smallest representation, okay, and see if it gives something interesting. Okay, so that's the ideal. And why is this called ideal? It's because in view of trying to give examples of Langlands functorial lifting, Langlands functorial lifting is something like that. Okay. All right. Okay. So that is local. So in the global setting, what you want to say was, let's say you have this setting at every place, then you can, of course, define. Let's say you can define a adelic representation of the adelic group. Okay, and then what you would like is you would like to have a automorphic realization. Okay, so let's say you have an equivariant map to automorphic forms on E, and then you can restrict to get functions on G and H, and then if you call this theta for element phi, you produce. After you restrict to G cross H, you have a function in two variables, and you can use it as a kernel function. Okay, it serves. It gives a map from say automorphic forms on G to automorphic forms on H. Okay, maybe you need Cuspidal. Okay, gives a kernel. Okay, so this function in two variables, it provides a kernel function for lifting functions on G to functions on H. Okay, so that's the general framework. Maybe I should do the other one first. Yeah. Sorry, just. Okay, so any case, that was the general framework, but does this, are there examples in real life that satisfy those, these expectations? Okay, so and point is there is. Okay, so in the classical theory of Howe, so Roger Howe sort of found one of these situations. Okay, and so let me describe that to you. So the main players. So is this, what is this G, what is this H, what is this E? So you start with a symplectic vector space. Okay, W, you start with a quadratic space, or if you wish, a symmetric bilinear space. And this gives you a pair of groups. Okay, this is my G, this is my H, let's say. And they map to group E, which is the large symplectic group obtained by taking the tensor product of W and V. Okay, this will be my E. So for example, you can take W to be 4-dimensional and V to be 2-dimensional. Okay, then you are going to get O2 SP4, right? That's an instance of this. And well, what is O2? Well, O2 is disconnected, its identity component SO2, is in general of this form, okay, a quadratic field, quadratic algebra mod F cross, okay? And so you see where the Howe-PS example is coming from, okay? So over there, they are working with O2, over here, they are working with SP4, okay? Okay, so that is the pair of groups. So the other ingredient we need is a representation omega. This representation depends on some piece of data, some additive character of your field, non-trivial. But I'm going to ignore this in this lecture. Just okay, it's what people call a Bay representation. Okay, so I don't know whether it's an unfortunate or fortunate fact of life is that, I should give you a representation on this group, for example, okay? However, this guy is not a representation of this group, but of a double cover. Okay. Let me make a few remarks about this Bay representation. I mentioned just now that you want to take a small representation, right? But maybe you don't want to take trivial, okay? So this guy is the next smallest. Okay? It is infinite dimensional, but there's some measure of dimension, which I will allude to in my lecture 2, under which this is considered the next smallest, okay? Now, there's a disadvantage that it's not really a representation of this guy, right? It's a representation of this double cover, okay? So you might say that then maybe we shouldn't consider this. We should discount it. We should go to the next smallest representation of, which is actually a representation of this group. So if you do that, right, then what happens is that it's already too big. Okay, it's already too big. With this correspondence is no chance to be in a graph or a function. Okay, and so because of that, you just accept this. Okay, and okay, so I've told you one point of view of this Bay representation is the next smallest after the trivial representation. Of course, another way to think of it, and sometimes the name of this representation is the name that Roger Howe likes, is the oscillator representation. Why? Because it is a representation that arises naturally in quantum mechanics from the analysis of the quantum harmonic oscillator. Okay, so indeed, the mathematical way in which this representation arises, when people introduced this representation, was through the representation theory of Heisenberg group, and from there, you arrive at this guy. Okay, so there's this representation comes from physics, if you wish, and because of that, you want to think of it as a natural guy. It's a representation that nature gives you. Okay, not something you create on your own. So you accept it, okay? Now it's a deep mystery of nature why it doesn't come here, but it lives there, okay? I don't know. Okay, but this creates a bit of a problem, right, to implement our general framework because we have this map iota. But, you know, we can't really pull back, okay, because of this. So, of course, in order to pull back, you have to ask yourself if you could leave this, okay? And so there's a discussion of this. Sometimes you can, sometimes you cannot. So this will analyze by systematically by Kudler, okay? And so the upshot is that if the dimension of V is even, there's such map exists. It may not be unique, okay? And that's why there's a need to be systematic to classify this. Okay, but if dimension V is odd, then you still have this diagonal arrow over OV. Okay, so you can always split over OV, but you don't have it over SP. In that case, you simply replace this group by MP of W, which is the analog of this metaplectic cover. Okay, so it's called a metaplectic group. Okay, so for this lecture, we'll just pretend we have, you know, we have a splitting and we fix it once and for all. So we can regard this V representation as a representation of these two groups. Okay. So in particular, I'm assuming dimension of V is even. Okay, that's that. Okay, so right. So I have written in my notes formulas for this V representations, but writing these formulas down is going to take some time, so I'm going to skip it. But I realize now what I should have done is to write down the formulas there before the lecture begins. Okay, so I will skip down formula. So the purpose of writing down this formula is to show you that this representation is very explicit. Okay, you have a model. Okay, so I won't write a formula, but I will say that what it is realized on. Okay, so that is there's this Schrodinger model again emphasizing a connection with quantum mechanics. Right? That this omega is realized on the space of function on a vector space. Okay, namely. You take your symplectic space W, right? You write it as a direct sum of two maximal isotropic subspace. Okay, so this is a bit decomposition. And then you can realize these Schwartz functions on a V tensor, say Y. Okay? Already you see, for example, it's very easy to describe the action of OV. If you have an element H in OV, you take a function phi in there, okay, give some variable to this, say y. It's just a very naive geometric action, okay, because OV acts on this part, right? So, okay. All right, so maybe that's all I'll say, okay? So the point is, it's a very concrete model. Okay, so these are our main players. What are the main questions? Okay, so I'm going to so just to remind, henceforth I will call G and H those two guys. Okay, so I'm going to ask these questions on three levels: the local smooth level. Okay. Maybe I should divide it properly. Here I'm going to look at the local L2 level, and then there will be a global. Okay. Okay. So for the local smooth, what happens is you take a representation, irreducible smooth representation of G. Let's say, okay, and you are going to basically you want to restrict omega to this and decompose, right? So you ask how many times this guy appears in this restriction. There will be some multiplicity space. That multiplicity space will inherit an action of the other group because the two actions commute. Okay. So you define the multiplicity space of sigma. But the definition is a bit in this way. Okay, so this is one version of the multiplicity space. Okay, the reason is because these are infinite dimensional representations. They are not L2. Okay, so they are smooth representation. When you restrict, what does it mean to say that sigma occurs in this restriction? Well, you can interpret it in several ways. One way is, does sigma occur as a sub-representation? Okay, another way is ask whether it appears as a quotient. Right? Then for each of these versions, there is a corresponding way of defining the multiplicity space. The version we are looking at here is about quotients. We are asking whether sigma occurs as quotients or not. Okay. So this inherits an action of H. Okay, so why is it related to quotient? So because note that by definition, right, you have a natural projection map from here to there, because this is G co-invariance. Okay, and then you can move this guy to the other side. Okay, then you're going to get something like that. Okay. Okay, so and this quotient is in fact the maximal sigma isotypic quotient. Okay, and I give this just for simplicity, I call this the big theta lift of sigma. Okay, now I realize that I can't really squeeze this here, so I'll just okay, so in a basic theorem in the subject, so-called Howe duality, is that this guy, for any given sigma, this guy has finite length. So this is a finiteness result. It's not too big, which is already saying that the representation, the very representation you take is, you're kind of in an ideal situation. Okay, the multiplicity space is not too big. Has finite as an H module. Okay, has finite length as H module, and in fact it has a unique irreducible quotient if it is not zero. Okay, of course it could be zero, right? Which we'll call little theta or pi. So small theta lift. Pi is sigma. Yes, sorry. Thank you. Okay, so so the consequence is that this theta, this small theta leaf, gives a map from irreducible representation of G. If you plug in sigma, I produce an irreducible representation of H. Well, except that this could be zero. So let me formally put a symbol zero. So if yes, unique irreducible. Okay, so I will get the point of this was, now this is saying that we are in kind of the ideal situation. Of course, there are things that could go to zero. And but let me make a remark. In fact, if H is much bigger than G, I mean, these are some symplectic orthogonal groups. So what I mean is the dimension of V is much larger than the dimension of W in a precise sense. Then we know that all these guys, all these big data leaves are not zero. So you can suppress this. Okay. You can suppress this symbol. Okay, so far I have given you an actual instance of this ideal situation in this general framework. Yes, yeah, correct. You can. It's completely symmetrical in G and H. So, for example, if G were was smaller than H in that context of that remark, okay, we say that we have a map. In fact, I've realized I forgot to say something. Can I want to pull it down again, okay? In the theorem, I forgot to say, in fact, it's stronger. So theorem continue that if you start with two different inputs, then the outputs are different unless they are both 0. Okay, if if they are non-zero. Okay, and what this is saying is that the map from irreducible G to irreducible H union 0 is injective. Okay, so yeah, so I mean, okay, so it's not really injective, right? Because many things could go to 0. Okay, but let's just say it's injective if G is much smaller than H. Okay. Okay. Or another way of saying it is that it's injective outside of the fiber of 0. Okay. All right, so I forgot to say this, and so because of that, you can go the other. So I guess Peter's remark that the same theorem holds going the other way is actually telling you this injectivity statement. Okay. Now, done that. Okay, so what is the L2 version? The L2 version is just very simple. So we have omega is realized on this Schwartz function on the V tensor Y, right, in the Schrodinger model. And in fact, it's a unitary representation. So you can complete, right? You can do a unitary completion. You get L2 functions. So on there, okay. And and we just want to know how this decomposes as a unitary representation. So let me say the theorem due to Yanis that so assume that G is smaller than H. I mean, okay, the group G is smaller rank, let's say, than H. Yeah, let me not. Let me just take smaller, okay, to be safe. Because sometimes it's okay to put equal, sometimes it's not. Then I didn't want to think about it. Okay, so it says first, how does this decompose? Okay, so maybe I call this the L2 version. Okay, so it decomposes into this just abstract nonsense at the moment, okay, but the content comes in saying that this is a Harris-Chandra-Poincaré measure. So in particular, the support of this unitary representation is contained inside the tempered spectrum of G. Moreover, because of the Howe duality, right, we can say something about this. It is either 0 or it's the small theta leaf. Okay, or rather, okay, and or let's take it smooth vectors or something like that. Okay. Okay. So so how do you decide, right, between this? So in fact, there is a more precise statement. The more precise statement is a decomposition of the L2 inner product. If you take two smooth vectors in there, in Raphael's talk, he explains what does it mean to have isomorphism like that, right? Okay, a concrete way of understanding this, this thing is to say that you give a spectral decomposition of the inner product. Okay, and then there will be this so-called relative character that would appear. This is Harris-Chandra-Poincaré measure. Okay, there will be this spectral, the sigma component of this inner product. What is this? Okay, so here's a formula where you sum over the orthonormal basis O and B, orthonormal basis of sigma. You pick any orthonormal basis, and then it's a sum. Let me put sigma here of terms Z. Okay, so what is Z? So you see, this part is explicating this isomorphism because I say, there exists an isomorphism, but what is it? Okay, so it's explicated by this. Okay, this is an integral over G of the matrix coefficients so it's explicit, okay? Explicit formulas, okay? Now, the point of writing this formula now is to note that, in fact, this guy has a name. It's called the local doubling zeta integral. And so I will discuss this next time, okay? Doubling, right? So, so it has appeared. So let me make a remark. So in fact, maybe say first appears in Genshuli's thesis work, 1987. And okay, so what did he do? Okay, so note that whatever this guy is, right? It has 4 inputs, okay, and it produces a number out of it, okay? So it's a linear form like that with some equivariance property, okay? And you see that it factors through this equivariance property. So it's G cross G invariant, right? So it will factor through, I guess, G cross G, G cross G cross H invariant. So it factors to give a Hermitian form on the big data leaf. Okay, and one can show, so a lemma, let's say, that Z sigma is not 0 if and only if beta sigma is not 0. So at least this is okay if F is non-Archimedean or F is complex number. When F is real number, this is not fully known. There's some cases that we don't know. Okay, but I'm sticking a non-Archimedean case, so okay, let's assume we know this.
It's only G cross H invariant, not more.
Sorry, you're right. So it is, this is G diagonal cross H diagonal invariant. Yeah, okay. I mean, there's a G cross G and H cross H action here, but I'm taking the diagonal copy, okay? Thank you. So, all right. So what, in this context, okay, so what Lee showed in this thesis work was that if, under this G, H much bigger than G hypothesis, actually, let's give this a name. This is called stable range. Okay, if in the stable range, this form thought of as a Hermitian form here, the kernel is precisely the it descends to a positive inner product. Maybe inner products are automatically positive, but anyway, on beta sigma, if sigma is unitary to begin with. Okay, so if you take in a unitary representation, so under this hypothesis, we know this is not 0, right? There was okay, and this actually gives the unitary inner product. So the main result is that if you put a unitary representation as input, this guy is also unitary. Okay, that was why he considered this construction. Okay, so that's the unitary setting. Now let me come to the global setting.
Do we have a similar decomposition in the Archimedean case for this circularities result?
Yeah, I think so. Yes.
As you said, like this thing may not work.
No, it doesn't work. What I mean to say was, look, there's this decomposition, right? I already tell you what this is. What about this guy, right? This guy is either 0 or dead. How do you decide? The answer is whatever that appears here, right, is non-zero even only if this pairing is non-zero. This Z sigma is non-zero. Okay, and then here I'm just saying that, but how do you decide whether this sigma is non-zero? Okay, is an integral, right? So you can try to compute, put in some vector and show that it's not zero. But what the purpose of this lemma is to say that the non-vanishing of this explicit integral is equivalent to a non-vanishing, abstract non-vanishing, right? Because this is somehow in a smooth, this question in a smooth category. Maybe put infinity. So this question is an abstract question, right? This is an explicit question, meaning there's an explicit function or some integral that you want to show is not zero. Whereas here, this is an abstract question. Okay, so you can decide whether something appears in there or not if you understand this abstract question.
Is this true for almost every sigma with respect to the Plancherel measure, even in the Archimedean case?
No, in a complex case, it's okay. It is true for all sigma. Yeah. Even for all sigma. But for in the real case, the point is that, for example, right, you have you look at orthogonal group, right? There are OPQs, there are many of them, okay? But you can divide that into two camps depending on the parity of P, let's say, right? And what you can say is that, so of course one direction is obvious, right? This implies this is obvious, but conversely, if this is no, okay, so basically the result is weaker in the Archimedean case, okay? But not in all cases. I mean, like, if you were to, depends on whether you go from symplectic to orthogonal or orthogonal to symplectic. Okay, so let's not discuss this. Yeah.
So
yes.
So the last line on the board on the right says theta sigma is unitary if sigma is unitary?
Correct, in this stable range.
What if, is that still true if you replace the word unitary with tempered?
No, it's not. It's not. I mean, in fact, when you go from a small group to a big group, the result is almost always non-tempered. Yeah, almost always non-tempered. It's only when the groups are roughly the same size, then tempered is turned to tempered. Okay, now, what about global? Okay, so in the global setting, this Weil representation, where you can think of as functions on this vector space, we need to give an automorphic realization, and there is one. Okay, so maybe I just say functions on G cross H. Okay, and it's given by averaging over rational points. So F, let's say, okay, and right. So I sum over Y. Okay. So this is analogous to the Zeta series in Raphael's talk, where you have a spherical variety. You take the Zeta series. Okay. So this is the original Zeta series. Okay, by the way, because instances of these are Zeta functions. Okay. All right. So now you can use this as kernel, right? So if you have here you have a Cusp forms in some sigma. Let's say sigma is now Cuspidal representation of G. Then you can use Zeta sigma as a kernel to define a lifting from functions on G to functions on H. Okay, and this guy, and then when you take the span of all this,
Integrating G or H?
G. Thank you. So if you take the whole, you let phi and f runs over where they are supposed to run, then you get a automorphic sub-representation. Of H. Okay, and what are the basic questions in this global context? I mean, they are just parallels of the local ones, right? So the questions are, is this non-zero? Because you have constructed some automorphic forms, but maybe it's zero. Okay, so you may ask, is it in A cups of H? Maybe is it in the square integrable, the automorphic discrete spectrum, so to speak. Okay? And then you may also ask what is it? I mean, if it is, say, non-zero cuspidal, you will ask what is it? Okay. Okay. Okay, so maybe to just make some brief remarks about this question. So about the what is it first. Okay, so here's a certain proposition. If you know somehow that this guy is not zero, suppose you answer the first two questions already. So, and you know that it lives inside the automorphic discrete spectrum, square integrable automorphic on H, then basically the Howe duality, the local Howe duality theorem tells you that this guy is irreducible. Okay. And then what is it? Okay, it is isomorphic to the tensor product of the local data lift. Okay, so in other words, the point is that suppose you have affirmative answer to the first two questions, then to the question of what is it is purely a local issue, because you just have to know what the local data lifts are, then you know what it is as an abstract representation. Okay. All right. Now let's look at the non-vanishing question. How do you show that what you have constructed is not zero? Well, we faced this question in the Poincaré series, right? Earlier we had Poincaré series and we asked, why is it not zero? And there we just evaluate at one point, right? Of course, if you want to know a function is not zero, you can evaluate at a point. If you're lucky, it's not zero, then you're done. Okay, but in fact, it is quite hard to evaluate a function at a point. It is easier to average a function over a bunch of points and to calculate that average. If that average is not zero, then the function is non-zero somewhere, right? And so one way of trying to detect whether whether this is non-zero or not is to average it over some, say, subgroup. Okay, so sometimes you can compute a Fourier coefficient. Okay, but here's another way. Okay, so we are going to compute so you take two such guys, okay, and let's compute the L2 inner product. Okay, the Peterson inner product. Okay, so there are two possibilities. One is that this thing diverges. Okay, if it diverges, the functions are certainly non-zero, right? Okay, so without loss of generality, assume it converges. Okay, because we are trying to detect whether it's zero or not. If it is, right, if the integral doesn't converge, the functions are definitely non-zero. Okay. Okay, so here's so we want to compute this, and this is so-called Raleigh's inner product formula. Okay. Okay, so the answer is the following form. Okay. There's some constants that I don't want to bother with, but otherwise it is a regularized Eulerian product of what? Of that. Okay. What are these guys? These guys are precisely the same guys up there. Okay. In other words, the same z's that appear in the L2 local L2 problem. Okay. All right. Okay. So I guess another way of saying it equivalently you can take this theta phi 1, and you can project it to the sigma part, okay, the sigma component, okay? Okay, so now you have two vectors in sigma, right? And again, up to some explicit constant, it is the product of, okay, what are these J's? The same ones that appear in the spectral decomposition of the local inner product. Okay. This was started by Rayleigh in the 80s, and then it takes quite some time to finally arrive at something like that. Okay. Now, why do I put a star here? What is this regularized product? It's in the same sense as in Raphael's talk. I mean, there's no reason why it converges. Okay, sometimes it converges, sometimes it doesn't. So, how do you make sense of this? Well, at almost all places where every guy here is unramified, you need to compute that. Okay, and when you compute that, you find that it is a local L function. Okay, so the way you interpret this is that you need to know that that when you take the product of those local L factor, I mean, it will converge when S is very big, but it has a meromorphic continuation. Okay, and then so it's in the same sense as in Raphael's talk. Okay, so let me make a remark about that, which is that this regularized product suitably interpreted is okay, so there's a number depending on the size of G and H. Okay, so actually it's quite explicit. It's probably dimension of V minus dimension of W over 2 or something like that. Sigma standard. Okay. Okay. Okay, so maybe the last 10 minutes or so, I make a. Let me. So this is I completed a traditional account, okay, of Theta correspondence. The point I want to point out was that there's no mention of Langlands program at all. Okay, this theory can exist on its own. You just take some representation, restrict, and decompose. Okay, of course, I say that here I refers to the this is where the first point where I sort of talk about automorphic L functions. Okay, and now so I want to just make a few quick remarks about this. You see, as a summary, right? After all this discussion, you see that all these questions come down to the following. So there's a global question, which is about L function. Okay, right? We want to know whether this thing is 0 or not. It comes down to whether this L value is 0 or not, for example. Okay, I'm assuming dimension of V is bigger than W, by the way.
+1, right? Is it dimension +1?
Maybe. I assume dimension of V is strictly bigger than dimension of W, so that this is at least half. Okay? For example, if V is 2n plus 1, this is 2n, then I'm exactly at half. I think this seems okay to me. Okay. And then, of course, there's the local question, which is, this is the abstract, the smooth local problem, and what is it? So basically, we come down to these questions. Okay? One of a global nature and one local nature. Okay, so I think this is where like the Langlands, local Langlands correspondence is helpful, because when we ask this question, we are basically asking, what is this map locally? What is the fiber of 0? That's what this question is, right? And to answer these questions, it's very helpful to have a classification of these guys, because otherwise it's very hard. You don't have the language to express the answer. Okay, so this is where at this point that it's helpful to have the local Langlands correspondence. Okay, I want to jump to this point, the relative Langlands program. Because as described in Raphael's talk, the relative Langlands program is about spectrum of spherical varieties. Okay? Theta correspondence is not really the spectrum of spherical varieties. It is about spectrum of the Weil representations. Yet, you can see that the way the results are presented here, there is a clear parallel. So, which you can see in this table, okay? So here I just say, what is the problem? Okay, problem is to understand spherical variety spectrum of this, right? Here we are looking at spectrum of Wave representation. In relative Langlands, there was a dual data. Okay, there's a dual group of X, and there's supposed to be a map like that. And in the local Langlands case, yes, in the Theta Correspondence case, yes, the answer is, I didn't get to it, but in fact, from the local, anyhow, there's also something like that. So anyhow, you can see that there's somehow a parallel, okay? In the relative Langlands, there's some L function that controls how the inner product of, like this inner product, right? Is supposed to be, again, this is a regularized product, and it should be an L value. What is the L function? It's some L function attached to a representation of X check. Here, our L function is something like this. Okay, so there's somehow a parallel, and the question was, is there a framework larger than spherical variety, which also includes Theta correspondence? Okay, and so I will conclude with just saying that, well, yeah, there is now a proposed, somehow extended, let's say, relative Langlands, which says that, okay, because the point now is this, right? So if you take this point of view, these are some G varieties, some G modules. Let's say you think of that as G modules that occur in nature. So it's this. So the question was like, what G modules should the relative Langlands program be concerned with? So initially conceived in Sakularity's Venkatesh book was spherical varieties. Okay, but now there's a proposal by, which I guess will appear in the book of Bensby. Sakularities and Venkatesh, that this G module should be G modules that arise as quantizations of Hamiltonian G varieties. Okay.
Good Hamiltonian G varieties.
Yes, certain. Okay, I quickly give some examples. What is Hamiltonian G variety? M. So it is a symplectic variety. M is a symplectic variety. So it's equipped with a non-degenerate closed symplectic 2 form. Of course, it has a G action. Okay, and then the Hamiltonian part is saying that there is a certain, it is equipped with a moment map to the Duality algebra. Okay. So these are things are the setting for classical mechanics. Okay. So these are objects that are studied in classical mechanics. Although Newton probably won't recognize it. And then the process of quantization, right, is to, you want to pass from classical system to quantum system. What should what are these, what should this data be replaced with? So what you should get is a unitary representation of G. Okay. Now, to give two examples, okay, maybe I give 3 examples, and then I will stop. First, what's the standard example of a symplectic variety? The easiest one that comes to mind, a symplectic vector space. Okay. It has an action of a group G, which is a symplectic group. it has a moment map. If you give me a vector W, I have to produce a linear function on X, which means if you give me an element X in G, using these two symbols, I have to produce a number, and I guess X. Okay, this is the symplectic form on W. Okay, what is the quantization of this? I should say one way of quantizing that is the following. The standard way of quantizing is that you take a Lagrangian submanifold, and then roughly, right, pi m should be functions on that Lagrangian submanifold, or sections or line bundles on that, or something like that. Okay. Now, in view of this, right, if we try to apply this, we would write. We had our Witt decomposition, right? So Lagrangian just means maximal isotropic subspace in this case. Okay. So that's my X, and so whatever this pi W is, it should be L2 functions on one of these two. Okay. And have we seen such a thing? Yes, it's the Weil representation. Okay, so we want, of course, there was this curiosity of nature that it doesn't live on SP, but it lives on MP. Okay, of course, you can change this to MP.
Or you can change it to a dual pair, like.
For example, yes. Okay, so that's the simplest example of a symplectic vector space. And here's another one. Take M to be the cotangent bundle of some G variety, for any. Okay. It has a moment map, which I don't have time to do. And now, what is a Lagrangian? This is a vector bundle over X. So you have the zero section. The zero section is a Lagrangian. Okay, so when you quantize, according to this rough scheme, right, you should get L2 functions. If X were a spherical variety, these are the things that are studied in relative Langlands. Okay, so maybe just to give one last example, if you have a co-adjoint orbit, okay, an orbit inside the dual of the Lie algebra, it has a natural structure of a symplectic variety. Okay, and so one expects that one should associate a unitary representation. Because it is homogeneous, it's one orbit, so we expect the irreducible representation, the representation to be irreducible. Okay, so what I want to say was the so-called orbit method or orbit philosophy would say that there should be a map from here to there. Okay, to every element here, a G orbit, co-adjoint orbit, you should associate irreducible unitary representation. Okay, of course, for nilpotent groups, this works perfectly, but in Lucas Mason Brown's talk, he discussed a bit about progress in this direction. Okay, and okay, I think I stopped. Okay.
Thank you. Any quick questions before we go into the Q&A session?
Should we mention the name of Jeff Adams regarding this dual group for the Theta Correspondence?
Yeah, so we should. So in fact, I basically annexed the second part, which is interaction with Langlands program. Okay, what I meant to say there was to answer this question, right? I said that it was helpful to have a classification like local Langlands. And then I'm going to illustrate this just by the unramified representation, because there you kind of have the local Langlands, right? Just semi-simple conjugacy classes. Okay? And then it is the case that when the groups G and H are unramified, the Theta leaf sends unramified representation to unramified representations. So you can ask, how do I describe this map in using Satake parameters? Okay? And it is by this map, okay? So you take a semi-simple class in here, right? And of course, you just take the same class here, okay? But the question is, what is there, right? So assume that this is bigger than SP, right? So the dual group of SP is some SO2n plus 1, right? And this is some O2m, where m is very big, okay? So you are supposed to put SO2n plus 1 into O2m. Okay, so maybe write it down, it will be clearer. So you have a SO2n plus 1, which is the dual group of SP2n. You're going to map it to, say, O2R, where R is very, very big, okay, for example. So, of course, this thing sort of maps into there, but there's a lot of room left, okay? How much room? I guess it's 2R minus 2n minus 1, right? Oh, sorry, this thing goes there. Okay. So you just have more space. Oh, it goes there. Right. So, so you take your semi-simple class here. You're going to put it there, and over here you are going to put this p to some power, and it's just decreasing. Okay. Symmetric 2r minus 2n minus 2 of this. Okay. So, and if you write down in terms of other parameters, you see that it is given by, I mean, the map from here to there is given in this way.
So you
And-
said that you have a map from SO2n plus 1 times SL2, and that's like the principal SL2?
Correct, yeah. So, yeah, I can do that.
Okay.
Yeah, so at the beginning we saw this general framework where you have G cross H inside of E, and
Yes.
then we really specialized to the case where E is the symplectic or metaplectic groups.
Yes.
Are there any other groups that fit into this framework?
Yeah, so what Roger Howe did, say at Covalis, one of his articles actually talks about, or maybe it's Gelbach's article, was to talk about, let's classify this pair of groups. So the pair of groups, the important thing about them is that they are mutual commutons of each other. And then so you can set yourself the question, say in SP2N, how can I classify all such pairs of reductive subgroups? And there's a classification there, and the construction is basically of the type I described. You can take a Hermitian form and a skew Hermitian form tensor, okay? But now, of course, you can say, what if I just take any group like E8 or something? And so people have thought about that for some time, and there was a classification over complex number over Lie algebra, okay? Of course, when you pass the group, there'll be rationality questions and so on and so forth. Yeah, so there is somehow an understanding. However, it is not like three-line construction like in the symplectic group case. Yeah, so in E8 probably you have a list or something like that. Yeah, and actually all these pairs of subgroups, they are used in the work of Springer, Tietz, other people, okay, who sort of exploit these subgroups to give constructions of exceptional Lie algebras. Okay, this was it.
Replace the metaplectic with some minimal, with a minimal representation in those cases?
Yeah, that's right. So again, it's the same philosophy. Suppose you take E8 and then you say, okay, I don't want the trivial representation. Then I ask, what is the next smallest representation? And this was first used by Kashtan, I guess.
Didn't you two look at it, or you and other people look at a case where with an S3 and a G2 and E6?
Yeah, no, so that is what we look at was basically in spin 8, or maybe the adjoint form of spin 8, so D4 adjoint, right? D4 is like that, and there's automorphism by S3, right? What is the fixed space? It is G2. So this is an example, but this is a finite group.
Okay, so maybe we'll have the 5-minute break, so come back at 35, and then we're going to have the question and answer. And let's thank Wojtek again for his talk.